So this problem wants us to minimize z equals x minus 2y over the given constraints. In order to do that, the first thing we need to do is we need to graph our feasible region. So we are going to take our first equation here and we're going to isolate y. We get 2y is less than or equal to negative x plus 8. Divide everything by 2, and we get y is less than or equal to negative 1/2 x plus 4. So let's go ahead. We're going to graph our line. My b is 4, which is here, and we're going to go down 1 and over 2 in this direction. And so we're going to draw our line a little squiggly on my graph and definitely not exact. But this roughly is what my line looks like, and we're going to graph below it. Now we're going to take the next line and we're going to isolate y. And we get negative y is less than or equal to negative 2x plus 6. But we need to multiply everything by negative 1. And when you do that, remember, the inequality switches direction. So we get y is greater than or equal to 2x minus 6. So let's graph this. 1, 2, 3, 4, 5, 6. And we're going to go up 2 and over 1. And so my line is going to be something roughly like this, and we're going to graph above it. The last two constraints give me my x-axis and my y-axis. And since we're going to graph to the right and above both of them, that means that this is my feasible region here. Now notice, my feasible region has 1, 2, 3, 4 corner points. And we need to find all 4 corner points in order to do this problem, in order to minimize and test the function. So the first one is easy. The first corner point we have is 0, 0. Okay, that's this one here. Next, we know what this one here is because that's just the y-intercept of our original function, and the y-intercept of that function was 0, 4. So that's our second corner point that we have. The third corner point, this one here, also is pretty easy because it is actually the x-intercept of this line here. So if we set y equal to 0, we see that this point is 3, 0. That would be in this equation here, setting y equal to 0. And then the last corner point that we need is this corner point here. Now, this corner point is a little bit more difficult to find. The only way that we really can find this, especially because my graph is not particularly pretty, is by taking the two lines that intersect it. That's this line and this line here. And by solving a system of equations in order to find that point. So we have, I'm going to use x plus 2y is equal to 8. That's the first line. And we have 2x minus y is equal to 6. Now you can solve this either using substitution or elimination. It doesn't matter. I'm going to solve it using elimination. So I'm going to multiply this entire equation by 2. We get x plus 2y is equal to 8. And we get 4x minus 2y is equal to 12. So when I add these equations together, the 2 y's cancel. I get 5x is equal to 20, and so x is equal to 4. If I plug that back in here to my function, I get 2 times 4 minus y is equal to 6. I subtract it, and I get y is equal to 2, which means that I get the point 4, 2, and that is exactly this last corner point here. So now I have all 4 of my corner points. Again, 3 of them very easy to find, but in order to find that fourth one, you have to solve a system of equations. Now that we have our 4 corner points, we can go ahead and we can test our z in each of those corner points. So let's see what we've got. Here we've got z is equal to 0 minus 2 times 0, and that just gives me the value 0. Here we've got 0 minus 2 times 4, and that gives me the value negative 8. Here we have 3 minus 2 times 0. That gives me the value 0. And here we've got 4 minus 2 times 2, which gives me the value 0. So go back to your original problem. The original problem is looking for us to minimize the function, and the value here that is least is -8, which means that the function is minimized at 0, 4, and its minimum value is -8.